Good evening, everyone. Hello. Hi. I'm going to stand over here because if I stand over here, you're not going to really see that much of me. And just up to me. First of all, Ken invited me to come back and give a lecture. I gave a lecture, the same topic, last year at the Ocala facility. And when he invited me to come back this year, I said I would really like to do it, but I want to do it with my colleague, Bill Clancey, whom I met through Ken, and with whom I've enjoyed a really nice and different collaboration over the last year and a half. So I thought it would be kind of fun for us to do this as a tag team tonight. And we've been cautioned about staying on time, so we're really going to try and do that. What we want to do tonight is share our experiences with you in ocean exploration and space exploration. Ocean exploration is changing. When I started out exploring the ocean, I got to go out to sea a lot. I was able to dive in submersibles. It was a lot of fun, and it's still a lot of fun. But things are changing because funding has dried up. It's very expensive to maintain and operate a research vessel. And the organization, the agency, the federal agency from which we get a lot of funds, NOAA, has decided that there's a new paradigm for ocean exploration that they're going to use. Scientists still go out to sea on ships, and they still get to explore using, well, one submersible. But more and more, we're switching to the opportunity to explore using telepresence and robotics. So we're going to talk a little bit about our experiences in ocean exploration and in space exploration, planetary exploration, and share some of our perspectives and I guess maybe biases too from my standpoint. Okay, so the oceans cover, really it should be planet ocean, not planet Earth, cover more than 70% of the Earth's surface and 95% of the biosphere, where things live on Earth. Only 5% of the ocean has been explored. So there's still a lot to explore. And ocean exploration is about going to these places where we haven't explored before, discovering new things, going to places at different times, doing them in different ways. But I want to point out, because this is a criticism of explorers, it's not just kind of, well, let's see, where do we want to go? Let's go to the Bahamas or Hawaii or something. It's very disciplined. It's very systematic. It's really the beginning of that continuum from exploration to discovery to hypothesis-driven research and so on. So it's part of the scientific method. When I teach the scientific method to 100 third graders every year, and that's what I tell them. These are the observations that you make that help you to formulate the research questions that you want to ask. All right, we're going to have a quiz. I want to make sure we're going to start right off. Okay. Does anybody know where the deepest part of the ocean is? I can tell right now this is a smart crowd. Okay, it's the Mariana Trench. Okay, these are getting a little bit harder. How deep is it? Anybody want to guess? Yeah. Okay, it's pretty deep. Okay. How many explorers, how many human beings have been to the bottom of the ocean, the deepest part of the ocean? Two, I'm hearing two, I'm hearing three. Three. It's three. Okay, so in 1960, the Trieste went down to the Challenger Deep with Jacques Piccard and Don Walsh. Jacques Piccard passed away, but Don Walsh is the man on the right-hand side of that photo, and he's congratulating Jim Cameron, the producer, did you know Terminator, The Abyss, all of those, who built his own submersible that went down to the Mariana Trench in 2012. And just for perspective, you can see the Trieste over to the left and the Deep Sea Challenger over to the right. Deep Sea Challenger is 24 feet long, and the place where he sat was like in there, and where Don Walsh and Jacques Piccard sat was in that little sphere there too. Very cool. Now, there have been other vehicles that have gone down to the deepest part of the ocean, but they've been unmanned. So there was a remotely operated vehicle the Japanese operate called the Keiko. It made, there were 3 expeditions there, made a few dives during those 3 expeditions. Woods Hole had, in fact, I should even say Keiko, JAMSTAC had Keiko. Woods Hole had Nereus, which was a hybrid, autonomous and remotely operated vehicle. It also went down to the bottom of the Mariana Trench, I think just 1 dive. And there's a JAMSTEC, the Japanese science organization, has a deep probe that they still have. Keiko was lost. Speculation that the tether was cut because they're tethered to the ship. And Nereus, which was, I think, operating in autonomous mode at that time, we think it imploded. So yeah, so it's kind of dangerous to work down there. The pressure that down at that depth is more than 15,000 pounds per square inch, 1,000 times more than what the pressure is right here. We're sitting right here. So why do we explore? And I get a lot of my funding from NOAA, and one of NOAA's kind of like taglines right now is that NOAA is the federal agency's environmental intelligence agency. So environmental intelligence agency. So we explore because there are a lot of threats that are happening in our oceans right now. There are threats from overexploitation, from pollution, from, here are the code words for climate change, increasing temperatures and changes in ocean chemistry. And what we're trying to do is kind of get a feel for what's happening down there, learn what these stresses are and how they're impacting the ocean environment, so that we can consider what's going on in the future and how do we deal with that, how do we adapt to that. So it's not only about survival of the oceans in many cases, in a lot of cases it's about survival of us as well. This photograph is of a deep coral reef, and the coral is called Lophelia, really beautiful thickets. Really threatened by trawling, shrimp trawlers and so on, and they're areas where there are important nursery grounds for important commercial and recreational fisheries as well. We explore, and by the way, these, especially in the deep ocean, you might say, why are we going to the deep ocean? Why would anybody want to go that deep? Well, these organisms that live that deep have evolved over hundreds of millions of years, but that doesn't mean that they can adapt quickly to the stresses that we're putting on in a very rapid way over the last, 50 to 100 years. Understanding our past, where you can explore shipwrecks and their time capsules. They preserve a single moment in time. I've been working for many years on the discovery of marine natural products, chemicals that have been derived from marine organisms that can be used to treat diseases like cancer and inflammatory diseases, infectious diseases. And this picture over on the right is of a sponge that grows in the Gulf of Mexico and is the source of a very potent anti-cancer drug. So there are many animals in deep sea habitats that are sources of novel chemicals with pharmaceutical applications. Okay, so I'm going to just step you through what telepresence is bringing to this whole equation. And I'm going to go into more of these in detail, but the basic idea is you take remotely operated vehicles, and they can be autonomous or tethered to the ship, and sensors, and you deploy these from research vessels. You can map the ocean bottom, you can take video images, you can get other data in real time, and that's something that's going to be important when we talk when Bill gets up and starts talking about planetary exploration. And then you have to transmit those data and images and that information back to explorers on shore. And again, I'll go into a little bit more detail on this. And then the idea is, at least with ocean exploration, is that you identify areas where you can go back later to do more in-depth research, no pun intended, and engage the public. Engage the public, engage the public. That's why NASA, one of the reasons why NASA has done so well. They've had a really great program to engage the public so you can participate in discovery. Okay, so what do you need? Well, you need a cruise plan, and you need money so you can execute that plan. At least for now, you need ships. And the reason I say that is that as the technology develops, you may be able to deploy these vehicles and platforms from shore. It's going to be a while before you can do that. Right now, there are 2 research vessels that are specifically focused on exploration. NOAA operates one. It's called the Oceanus Explorer on the left. And Bob Ballard's group of the Ocean Exploration Trust operates the other one. It's called the Nautilus. You need the ability to telecommunicate, to take those images from the vehicle, the robot, if you will, and transmit them back to shore, back to the other people who are participating remotely in exploration. You need your robots, and here you can see, actually, the way the Oceanus Explorer works is usually the day before, or maybe sometimes weeks before, they use the ship to do sonar mapping of the bottom so they can pinpoint the areas that they want to do more exploration on. I have to stop saying research. And then the Oceanus Explorer, NOAA's exploration vessel, uses a remotely operated vehicle which is tethered to the ship and has the ability to go down 6,000 meters. So you can see on the left-hand side a picture of the ROV when it's being launched, and right down at the bottom when it's on the bottom. You need a process to collect the images and then be able to transmit them back to shore in real time, and you need the expertise to be able to do that and to be able to make decisions on the ship. So this gives you an idea of the control room on board the Oceanus Explorer. There are people out there too, but there are not that many scientists. There are usually 2 scientists, 2 people, usually a geologist and a biologist, who can basically referee and make decisions about where they're going to go, although there is a cruise plan in advance, but also to be able to kind of like field the questions that are coming in from the dozens or hundreds of participants back on shore. But most of the staff out there are related to the robots. They support the robots, so the ROV, or the satellite communications, or the mapping using the multi-beam sonar. And you need to be able to engage participants on shore and be able to communicate, and this is really important for us to be able to communicate in real time so we can have some input into how the expedition is going and maybe make some minor adjustments to the plan. It's kind of cool for me because up until about a year ago, they would say, oh, and I work on sponges. Up until a year ago, they would say, oh, sponge, keep going. Oh, sponge, keep going. So now I've been able to say, hey, when you see that sponge, that's really important. Let's take a look at that. And now, on the last cruise that they had in Hawaii, they spent a lot of time getting amazing images and, oh my God, even a collection of sponges as well. So we're really excited about that. So it can be as sophisticated as this shore-based system that's at the University of Rhode Island, which is basically called their Inner Space Center. And that's where all of the satellite communications come in and then are distributed to smaller exploration command centers like this one, which is at my institution at Harbor Branch Oceanographic, and at about, probably about 10 other places worldwide. But you can also participate by, just by sitting at your computer and logging on. Now, you can't participate in the chat room unless you're actually involved in the mission, but you just register for the mission, and if you have scientific credentials or a real interest in participating, you can usually get permission to get involved through this chat room or an event log, and through our Exploration Command Center, we can also pick up the phone and talk by satellite phone. So if there's something that's really interesting, I can pick up the phone and call and say, hey, can you take a look at that? If you're on your computer, you have Internet 1, there's going to be anywhere from a 20 to 40 second delay. But we have Internet 2, and at the Exploration Command Centers, that's a faster Internet, and it's literally like a 2-second delay. So if I'm just looking at it from my computer, by the time I say, hey, can you go back and check out that sponge, they've already gone on to some really cool, like fish or something like that. And the other thing that's really important here is that for this particular type of application with NOAA, because it's funded by a federal agency, and the paradigm that they have for this is that they want to engage as many scientists as possible, the data that they collect are publicly available. So that means that, for example, you can go to a website, and this is what's called the Digital Atlas, that NOAA maintains, and you can actually go to, it's searchable, So you can search by year. I have all of the cruises for the last, I think, maybe 5 years. That were exploration cruises. Now, it wasn't just the Okeanos Explorer. There are some other expeditions that we go on. Like, for example, this year we had an expedition and we became one of NOAA's signature cruises. So it was an exploration cruise, and so we're on that map as well. We were kind of like down in this area. In this cluster, you can see there's a lot here in the Gulf of Mexico, a lot up the East Coast, around Washington, D.C., where the decision makers and funders are. And then there was a really nice set of cruises an expedition this year around the Puerto Rico Trench, and then that was in May, and Bill participated in that. And Bill also participated in a recent expedition to Hawaii, but participated via telepresence. But you can go on and click on any one of these dots. You can select what kind of theme you're interested in. You can just click on one of these dots and you can get access to the data. Now, this is different from the way we've operated in the past. So there are a lot of changes. It's a new way of exploring, because in the past, and because we have some funding to continue to do expeditions, I basically get to draw up a cruise plan. I have objectives. We select our crew. It's only those people who get to go out to sea. We don't have telepresence, so we can't share what's going on in real time. We can we do blogs, and people can kind of join chat rooms and things like that, but it's not in real time. And the data basically are our data until we choose to release those data, and it's usually a couple of years, because we have scientists who are working on their research and want to publish, and we have students who are trying to get degrees using the data. So the data are restricted. But if you participate in an Okeanos Explorer expedition, all of the data are publicly available. So the burden is on you then to interact with the dozens of people who are on that cruise, virtually, and you can see them. They're in the chat room. You can see who's participating, and then try and say, okay, and because you don't, as a scientist, you don't want to get scooped. You don't want to be working on something and you're just ready to publish, and then you find out, oh, geez, they just published that. And that's one of the concerns about having publicly available data. So, and as an example, on this last cruise to Hawaii, again, they took a lot of photos of deep water sponges. So, be still my beating heart. It was so exciting. And they took samples. That's the other thing. Part of NOAA's paradigm is we don't want to stop and pick up samples. The scientists take too darn long to collect the samples. What we're try and do is explore. And but they took samples this time. So I've been in communication with the scientist who did that, and who, thank goodness, has already worked up a lot of the data, but has agreed to work with other experts to put together a publication on deepwater sponges from Hawaii. If you search in the literature for deepwater sponges from Hawaii, there are two. Actually, they're not even deepwater. There are two sponges. So if you go into the literature for sponges from Hawaii, there are two. That's it. And now we've got lots more, like at least 20 more, and probably more than that. So I would like to now turn this over. This is the tag team part of it. I'm tagging.
All right, great. Well, Shirley will be back. And some of these issues that Shirley and her colleagues are encountering have been part of the planetary science community for many decades. But this ability to explore remotely, having a robotic surrogate be a physical surrogate for you, that we don't have people down at the bottom of the sea or on Mars, is relatively new. It's only been possible for a little more than a decade for us to have, like in the case of what Shirley was showing you, the live television or these robots on the surface of Mars. And so we're really learning by doing, and these expeditions, whether they're on Mars or the Okeanos Explorer, we're learning how do you plan, who should be involved in planning, how do you control robotic manipulators, and how much time should you take in doing your analyses and staying at one place and trying to cover distance. How do you label and store data that covers miles and miles, or and might not be used for many years by other scientists and as part of dissertations? And how do you engage the public? And now that with social media, there's all new ways that we can bring this science to the desktop. And we're just really beginning to grapple with, well, what's been gained? What can we do that we couldn't do before? And what's been lost? What is lost by the oceanographers not being able to go to sea? To be there in person. What difference does that make? What difference would it make to be able to send astronauts to Mars? And how would they interact with their community back at home? For Mars, we've had no choice. Planetary science has always been done remotely, and that includes the flybys, like the flyby of New Horizons past Pluto this past summer, and the orbiting spacecraft that we have, let's say the one around Cassini, around Saturn, that's been there for many years. But for undersea, the scientists are now being displaced. They're being told, you can't have your submersible, you can't go. So it's raising an issue of how can these two different areas learn from each other, and where are we going in terms of field science as a whole in how scientists relate to this robotic technology. So I'm going to talk about Mars. I'm going to go through fairly quickly and give you a sense of what we're doing on Mars and how we're using robotic systems. And then we'll finish up the talk reflecting together on lessons learned and difficulties. So here you have a map of Mars. It has roughly the same land surface as the Earth, but from what Shirley said, the oceans still win. But it means we have a lot of territory to cover. And I've put on the map here what you just saw in the last slide, and I'll come back to a moment, is Gale Crater, where we have Curiosity, the Mars Science Laboratory. And you've certainly heard about Opportunity and Spirit at Meridiani and Gusev Crater, the Mars exploration rovers, and I'll go through those in a moment. The real precursors were, well, Pathfinder was the first prototype test back in 1997 that showed that it was possible for us to program these rovers every day and have a science team tracking and participating. These first major projects were Vikings, 1976, Viking 1 and 2. We didn't give them cute names back then. They were just 1 and 2. And my little quiz for you is what is this, this cross up here? Does anybody know what that's marking? If you've seen the movie The Martian, that's the Ares 3 landing in fiction. And he goes down to Pathfinder to recover the communication gear, and then goes over to Schiaparelli Crater, where they had another Ares 4 waiting. So Mars is very real for many of us, and the maps and all of that fiction are real places. You sometimes hear the Mars exploration rovers called as robotic geologists, but they're laboratories. They're mobile. They're programmed remotely from Earth. They're programmed every single day, or every sol, as we call a day on Mars. And they are very sophisticated computer laboratories with a number of instruments that can do spectral analysis, determine the elements, the atomic composition. The latest rover, MSL, can determine organic compounds and different isotope mixtures, sophisticated instruments that geologists and biologists do not take to the field. And so here we have the paradox. Not only are the people not there with these instruments are normally only used in a laboratory by specialists. And you have people on the team who have never been in the field. They're laboratory scientists, and others who have never used the instruments that they're now helping to program. So the traverses of the Mars exploration rovers, Steve Squires has called them our first overland expeditions on another planet. And that's what they are. We've been traveling and getting to know this landscape in this case for Opportunity, for over, getting on to 12 years. It had a 90-day warranty. And it's amazing. It was, the success criteria was 900 meters, and we've gone 42 kilometers. And so the engineering is really incredible. They hadn't counted on the solar arrays being blown clear by dust devils, and that's really been our savior, because we need that. We do have to park the rovers at a certain angle in the winter, the Mars winter, so that they can, the power will still be there and maximized by the angle of the arrays. And Spirit actually got itself stuck, and we were unable to get it into a safe spot. And we last heard from it after it did, it operated for over 5 years. So these are major expeditions that we have been doing on another planet. It's really why I called my book Working on Mars. We've been working on Mars. And this is our more recent rover, the next version, the Mars Science Laboratory. It weighs almost a ton. It's about 9 feet square and 7 feet tall. People describe it as the size of a Mini Cooper, which I guess I've seen once or twice. But to think about the scale here, those wheels are 20 inches in diameter and 16 inches across. So it's really big. It's thermonuclear electric power, so we don't have to worry about the cleaning of panels. And it has a whole suite of very sophisticated instruments that go beyond, much heavier than what we were able to do for the Mars Science Laboratory, or for the exploration rover. This is what we're exploring. We landed in Gale Crater within 1.5 miles of where we had intended to go. We went over 300 million miles, and this thing lands completely under program control in those last moments, and I'm sure some of you have seen the video. And what we wanted to know is the climatological and geological history of this area. What is the role of water in the formations that we see here? Were conditions ever right environmentally, including the atmosphere, the water, the pressure, and so on, for microbial life to form? So we now know, as the study has proceeded, that there was a lake bed there for quite a while. We can see the sedimentary rocks that formed. And as Grotzinger, the head scientist at the time, put it, the water was good enough that you could drink it. So it wasn't the acidic water that we've seen with Meridiani, in Meridiani Planum with Opportunity, but this was water that was even better for life conditions. So you see this amazing spot here, Mount Sharp, over 3 miles high, and we're actually not going to go to the top. There's a lot of sediment, but we're exploring just to the lower reaches of it. We've gone over the area there that you see in green in the first 3 years, and we now have an extended mission. We're about to cross over into the really interesting areas of clays and sulfates with layers that will tell us a lot about the water on this in this area. So I wanted you to see, to really understand about the what it's like. Each one of those yellow dots, think of it as a meeting or a telecon. So the science team had to decide for each spot, are we staying or are we going? Which instruments are we going to apply? What rock are we going to apply spectral analysis to? Which images are we going to take? What's going to go into the chemistry labs? What are we going to zap with our laser and then look in the telescope to determine what the chemical composition is and decide whether we should go in closer to analyze more? So almost roughly on the order of 1,000 meetings involved for this in a period of about an area of about 10 miles of exploration. So why is this so difficult and so tedious? It's because we can't joystick the rovers on Mars. We can't control them the way the scientists would be able to control the Deep Discoverer, the ROV, under the ocean. They could technically control that from Rhode Island. and there'd be a delay of a second or so, and it would be sufficient for people to have hand-eye coordination to control it. But for Mars, as the planets are moving, the light speed communication one way is between 4 minutes and 24 minutes. And so you have to double that in terms of you say go forward, and as much as 48 minutes later, you would get an image back showing you exactly how far forward it had gone. And so therefore, if it were moving along at all by its own control and you needed to stop it, you could find yourself hitting an obstacle. So this is why we send a program, what we used to call batch programming when I started computer science in the 60s. And every day we send a program up and we get the results back. And I would mention another character, that we're not even in the same plane exactly. So there's a lot of orbital mechanics and considerations here. So this gives you a schematic of the whole process. Every morning, Mars time, and this was the Mars Exploration Rover that was operating strictly according to sunlight. These are Mars time dates of the local rover. We send the program up, it works, and then sends us data back. And then the scientists arrive about an hour before most of the data is going to be returned, and they start having meetings and they're reviewing the data. And they meet among themselves and then review, well, which things might have to be retaken? What do they want to know more about? Should we stay or should we go from this point? How do we prioritize everything we want to do? How do we prioritize the data we're going to get back? The thing is way too slow to give us the data every day. What data do we need to have tomorrow? How much battery power is there going to be given the conditions of the solar panel? So they have to work with the engineers. They put together a plan, and the engineers then will have another shift all night long to test the plan, to run it in simulation mode to see that the robot's going to be safe. And so these scientists are used to working almost always alone out in the field. Geologists especially, are now working totally by consensus. Geologists, atmosphere, soils and minerals, chemistry folks, all thrown in together, and they're anonymous. You're not going to see who suggested we should move, who said that rock was a good one to study, and they were right about it. And then you have this public nature as everything, the pictures are appearing on the internet. Public, anonymous, and very different. So the way this is possible, and it was part of the real discovery of my study of the scientists, is they have to be able to place themselves in the body of the rover. They need to know, what can I reach today? What can I see? How far do we have to go? How many days will it take to get where we need to go? And then they need to in great detail, program the rover. And the way it's done is by taking a series of photos, more and more photos. As you get closer and closer, you have more and more detail, and you register the photo relative to the coordinate system of the body of the rover. So we know when they point and draw on the image like a yellow bounding box and say, take a pan cam, an image here, that can be translated into a computer program that will point the camera, set the filters and everything, and return that picture. And now you have to give it a name. And somebody's going to have to find that picture 2 or 3 weeks from now, the one who thought it was a good idea. And you're labeling places where the spectral analysis is going to be done. You see, it's quite a sophisticated orchestration that's going on. And it is an immersive experience for them. They have stereo that they can look at the images. And the nature of these instruments, like here you have the thermal emission spectrometer that is giving them chemical information, like where the iron is located. And the rover has been designed so it registers perfectly on top of the photographs so that you can see the landscape in a way that, like special eyeglasses, that you'd never be able to see if you were a geologist. So you see this paradox. They're analyzing like cyborgs as they look around, and yet they're all having to do it together, and they're not actually there. And so this is an example of what in cognitive science we call embodied cognition, of how in the imagination of the people, through the tools we've given them, they can, as Jim Rice said, put himself out there in the scene. scene. As the rover, I am 2 boots on the ground, and I look and think about, relative to my experience, what would I do? And then, how do I translate what I would do to something that the rover will do? How do I explain that to the engineers? And what steps do we have to go through? And it was always this perspective of being on Mars. And it's contrary to what you might think, that they're not there and the rover's doing everything. It's instead, we've provided a way for them to have what's called virtual presence, that they're on Mars. Now, the AI, the artificial intelligence, is mostly at the level of gathering this, picking up rocks or applying the drill rather, and obstacle avoidance and finding paths. So they program as much as they can, and then they'll tell the rover, proceed from here to over so much a distance in a certain trajectory, and the rover will then go very, very slowly, and it'll use its sonar and image analysis to decide how to steer. It also has a very primitive capability that you can program it to say, as you're moving, if you see a white rock, take a picture of it, but keep moving. So things like this, if you ever happen to see something like this, don't tell us 3 days later, send the picture. So Steve Squires said, with the robot being our physical surrogate, the scientists and engineers are the collective brain of the rover. So this was quite a surprise to realize we had built what we call in computer science a collaboration tool. We found a way to get all the disciplines to work together to do a holistic study of Mars, so that the atmosphere folks are talking to the soils and minerals people, who are talking to the biologists, and it's all one team. And Squires described it as one instrument, one team. And we're not going to have people fighting over who gets to use the hammer, who gets to use the microscope. It's all at your disposal. And then this now becomes a segue to our last part, because this is not how other missions are run. Cassini, there's those who own the icy rings, those who own Saturn, those who own the icy moons, and they have turf, and they will have to have time when you're allowed to use Cassini. It's like Hubble goes to another extreme, the Hubble telescope, time sharing basically. You sign up for a time slice. And these are we don't know how to do this yet with the Okeanos Explorer, which itself doesn't even have an assigned mission team, mission scientists. And so that's where my work with Shirley, kind of breathless experience, comes in. And so in September, I had a chance to spend a week when we had live video with the class, and to get an idea of, well, what's going on in this place called the Explorations Command Center. And so we know we want learning to occur. There's learning about, in this exploration process, we have students taking a course here. We want them to be learning basics in oceanography. And part of my research is understanding how conversations promote learning. So one of the things I was looking at that I'll show you in 2 very short videos is just looking at the conversations that occur and can be heard in the Exploration Command Center. So this first short video is to give you an idea of what it's like to be in that room, and Shirley showed you a picture of it, and you'll see more in a second. In the first video, all of the people who are speaking, there's just 2 people. There's the man and the woman, the geologist, and I guess one was a biologist, on board the Okeanos Explorer. And they're narrating for anyone who's gone running this on the desktop or in an Exploration Command Center, they're narrating it. You might not understand every word they say. I characterize it as like they're like professional journalists at a Rose Bowl parade, and there's all this stuff is coming by.
Well, and they're listening, and they're on their computers, and so we're seeing things as, oh, that's a hexactinella sponge, or that's a gorgonian, or that's, so they're saying, oh, and so-and-so said this is something, so they're narrating that as well.
And so you'll see in this short video, as I pull the camera back, our students are logging what's happening in a database.
A couple of different the anthromatic scroll, but this is the first that we've seen, I believe, on today's diet, unless you saw anyone while I was gone.
Well, we saw 2 little polyps that we thought might be a young anthromatic, but this is certainly the first one we're on.
video that we monitor. The video that we get is very high definition.
It's actually one of these issues about the data that the high-definition video can't be sent from the ship through the satellite. Even now, a month later,
right,
I don't have it. So that's I was hoping to put it in. The second excerpt is very different. All except one remark is made inside the group of the Exploration Command Center. I'm watching our time.
Yeah, I am too.
Sorry, move it along. And so I want to just talk you through very quickly. You're going to hear a faculty member who's running the class make a remark about the geological formation. And then, by coincidence, the scientist on the ship says, yeah, that's what I was thinking too, which prompts the PhD student who's behind me to say, yeah, to sort of make a joke out of it and say, yeah, of course, that's exactly what you were thinking. But it's very interesting to see because then, next thing, one of the master students asks a question about what are we seeing? And she never speaks up, and we haven't had these questions. So I'm very interested of how there was an icebreaker, really, of the faculty and PhD students speaking, that now we go into a dialogue.
Think how long that's been there and how clean it is.
Yeah, that's what I was thinking. I have a very...
That's exactly what he was thinking.
How would something like that form?
How did something like that form?
The example
That's
collection that we're
what a good question is. Like, a block, like, I mean,
shape is indicative that it hasn't been.
It's not
it could be a former dike, so that basically these lava flows come up and shoot out and very cool and form this kind of lava.
She then goes on quite a bit, and I also wanted you to see there how the rover, they refer to them as flying this thing, and I had no idea we were going to see such interesting geology. I'm interested in the geology.
Rocks. So there's some, to just kind of summarize a comparison of the way now we're starting to explore the oceans, which is really kind of at a very early stage compared to the way we're doing planetary exploration. So 3 main points. First of all, it's live. Okay, there's not a delay of hours. It's pretty much instantaneous. There are multiple science teams that have, and from all over the world, so any scientist who's interested can register, sign up, and participate. And then the remotely operated vehicle operates usually just about 6 hours a day. And when it was in Hawaii, it was a little bit, it operated on their time zone, so it was a little bit later on the East Coast, but there was still a lot of participation as well. And I wanted to raise one other point, too, because some of the things that we use, the vehicles and the platforms that we use to explore, are very much like the rovers. You have to, in fact, my husband kind of whispered in my ear when you were presenting, and he said, it's a lot like programming an autonomous underwater vehicle that's not tethered to the ship. So you can read all the specifics. I think one of the issues is being able to collect samples and trying to figure out, okay, can we get smaller and smaller samples that can take less and less time, or can you get to a point where you don't even ever need physical samples anymore?
So, as you saw, and to remind you of the contrasting perspectives, everything the scientists see coming from Mars is recorded. And so they're not getting anything live. But everything has to be fully programmable, and that included, of course, the landing, but the arm, the drilled, all of the laboratory analyses, the safing, and so on. There are raw images available on the web for the public the next day, but there's no samples returned. Talk about something that would cost $10 or $20 billion. But they're doing this remote atomic and molecular chemical analyses that are not, I think, even being dreamed of for undersea, because we have to do the analysis right there. The science team, we don't have 10 different science rooms that anyone respectable can sign up. We have a closed, what could be called an elite group that's chosen by the principal investigators and by NASA, and no one else is allowed in that room. And they are all going to publish together as a group. The rovers can't be picked up and repaired every day, but they go 5 or 10 years without repair. And they're also running in extreme conditions, in this case, extreme cold. And probably not surprisingly, it costs a lot more to build something with those kinds of capabilities.
Yeah, a couple orders of magnitude in terms of the cost. So what are some of the advantages of telepresence-enabled ocean exploration? First of all, You can go. I mean, I wouldn't have been able to go to to Hawaii or to the Puerto Rico Trench, and there are many individuals who can't go for a variety of reasons. Think about people who have physical handicaps who makes it very difficult for them to participate in expeditions at sea. They can participate now. So there's a broader engagement, learning in the science community, and also in the general public. And there's an increased pace and scope of discovery, because remember, I said we've only explored about 5% of the ocean. This gives us an opportunity to increase that pace and scope. Now, there's nothing that's going to preclude us from doing these missions of elite scientists who only have a few, it's not a broad participation. What's expensive is the telepresence part of it. There are ships. There are ships with remotely operated vehicles. There are a lot of ships with remotely operated vehicles. It's the telepresence, the ability to communicate in real time back to explorers and researchers on shore that really make this more broadly available.
Yeah. And all of these are true in different ways, in some cases, with the planetary science as well.
Right, and there's mentioned here, there's a stimulus for innovation, because we're really in our infancy in terms of developing new probes and sensors, and we have a long way to go in terms of being able to develop instruments that can survive in those hostile environments.
So showing you the Exploration Command Center on the left and the Science Assessment Meeting Room on the right. And actually, if you see, there's a very complex analysis that's being presented among the scientists, which is very different from what the scientists are talking. So there's a reason why the public is not in on all these meetings. You wouldn't be able to follow the vast majority of what's said. But both teams, both inner and outer space, are facilitating cross-disciplinary collaboration. Both are seeing how shared viewing is promoting conversation, though in the case of for planetary science, it's only among the science team and not museums and schools and so on. Both are attempting to use social media and might still learn from each other in ways of borrowing methods there. But really, only for the Okeanos Explorer do you have chat rooms and video calls where the whole scientific community that has signed up can participate in saying, where should we go tomorrow? And what sample do you want us to stop now? You have that ability, and it's definitely not possible for planetary science for an arbitrary geologist, say, to be involved. And robotic exploration may motivate and justify human missions. That's a big part of what we're doing on Mars, but it's almost the inverse of what we're doing with the ocean, which is going the other direction. Yeah. So each side has room for improvement. As you say, it's just just over a decade. You can tell from the maps I showed you, and the scientists are first to say it's glacially slow. The geologists would have been way up on Mount Sharp within a matter of days, for sure. And that's what they want to do first. And then they survey, and so they're unable to work the way they're used to. We have a gigantic area. We're covering, if you saw, just an inchworm size of that 96-mile wide crater. There's going to be things to study there 100 years from now that we missed, and they could be 10 meters off of the path. And there's no ability to do sampling, which is really why we need to bring things back to Earth, because the instruments that we have available and would use are too heavy or too large or use too much power to package them. We are interested in curating, saving samples and come back and get them later. That's what we're looking at in the next mission. They need to be able to drill much more. And this robotic automation, as you see, is just extremely expensive. But the science return is, there's no other way.
Yeah, and I think you can say pretty much the same thing in terms of the advantages, some of the disadvantages for ocean exploration via telepresence as well. Here we started out with human exploration, where I got to go in submersibles. A lot of other people got to go in submersibles. Now we're looking at a different way of doing things. There are pros and cons, but it's a new approach.
Yeah. So, if you want to get more information.
Okay, if you want to get more information, you can go on to the oceanexplorer.noaa.gov website, or just type in ocean exploration. It'll take you there. We also have a website for our Cooperative Institute at Florida Atlantic as well. And
for Mars, you can see where opportunity is today and where it's going tomorrow. And the Curiosity rover, it's all very open. and very easy to track, great maps. And you can go to my website to learn more about some of these studies. And I have to put in a plug for the book,
really
which I hope you'll look at as well. So thank you.
Are there any questions?
Thank you very much. The Swedes and the Japanese have long been experts in optics. Do you have international cooperation on telepresence research?
Definitely for the space planetary science. So Cassini has many, I don't know all of the countries, but it's at least a handful. And the Mars Science Laboratory and Mars Exploration Rover have instruments that were developed in other countries as well.
Right, and the same exists for ocean exploration as well. So there are international collaborations as well.
Yeah, it's essential.
Yep. Any others? Somebody right here?
Thank you. Is there another Mars Explorer mission scheduled, and what is it going to be able to do that the existing explorers can't do, or what's everyone's hope?
I was all ready to answer questions about curiosity here. Unfortunately, I don't think the Wikipedia has given all that. So I think they're calling it Mars 2020, and I'm really not able to tell you everything there. The one thing I do remember is that they're going to have a zoom lens that they didn't have the time to get on Curiosity. In general, they're able to target a little better now what the questions are. So I would be looking towards instruments that can really confirm some of those hypotheses about organics and water. But my best source is to say, check online. They might not have decided all of that. I mean, they're in a finalization phase, I would think. Yep. I do think they're going to be doing caching on that. I do think that was to be ready, be able to set materials aside, but I'm not sure that got on board.
When you talk about the 5% that we've explored, are you talking about
the bottom?
That's the bottom.
The ocean bottom, yeah.
So we've still got everything between.
Which is really where most of the things are living to, in that, and the plankton too. Yeah, we have a long,
that was one of the first surprises for me to realize that there's a volume. It's not just the bottom.
It's not just the bottom.
They're characterizing an atmosphere of water.
Right. The science I do is mostly benthic in the bottom,
levels.
But yeah, there's that. In some ways, that's a little bit easier to tell you the truth, because you can. Yeah.
Are you doing?
With the ROV, with a remotely operated vehicle, no. But there are a number of instruments that are deployed that take measurements. And so there's a large suite of sensors, drifters that take that kind of, and more vehicles are being developed that are programmable and that can dive down and take measurements. And yeah, so that's a very robust field of research and development. And there are these drifters that are deployed worldwide.
Yeah, they come back and they raise an antenna and they send the data to Shirley's cell phone and everybody else, and then they can actually reprogram to say, well, head now in this direction or go to a certain depth.
Take a look at Argo floats, ARGO floats. It's a worldwide distribution of sensors, and a lot of the weather data that we're getting comes from those. There was someone over there, and and then we'll get to you.
I was wondering, if you're unable to perform repairs on the Mars mission, how do you ensure that the instrumentation remains accurate? Like, you can't perform controls on it? Does it perform like itself?
There's some calibration that's possible. So I don't remember. Well, first of all, for visual, you have things that you've placed down. Like I read somewhere, there's a Lincoln penny from 1909 that they take an image of, and so they can focus and work out colors and so on. For the chemistry labs, I believe they have some blanks or tests that they can run through and be sure that they're getting what they expect from that known sample. And a lot of things are just trying to replicate on Earth. They build up a library of running things through and then trying to confirm in different ways.
Do you have a question over there as well?
Yes. What do you expect is going to be the biggest discovery on Mars that's going to be of real benefit to us Earthlings?
Well, it's hard to say. Do you mean emotional benefits or scientific benefits? And finding proof that what we would call microbial life had formed, and being able to determine its reproductive basis. I'm almost reluctant to say genetic basis, but there's a presumption, and then answering the big question: was it a dual genesis, so life formed independently, or did the life on Earth, or are we all Martians?
And what's interesting about that is that there's research that's being conducted looking at the microbes that are living. You go to the ocean bottom, and then you drill down, and you take a look at them, and there's a really interesting and diverse microbial community that's living in the rock. So, and really the reason, a lot of the reason that research was funded was to think about, give us some insights about exploring and probing for life on other planets. You had a question.
It sounds like the telepresence also leads to people wanting to commercialize the ocean floor. Do you see that happening? Are there any controls that are possible on something like that?
That's a really good question. And in the internet, it's a hot topic for international discussions as well, because right now there aren't a lot of rules governing high seas exploration. So I don't. Yes, there's the potential. It's being considered. And there are like UN-sponsored teams that are looking at governance of high seas and of mining, for example, seabed mining, and so on. So, yes, yeah, that's.
We have time for one more question.
Okay.
With the use of robots, is it really necessary any longer to send people either down into the oceans or out into space?
Well, certainly the planetary scientists, they don't hesitate for a second, say yes. And the reasons have to do with the speed and flexibility. As I said, there could be something that's just a little ways off the path that you've completely missed. Yeah. It'd be like Captain Cook missing Antarctica because it just happened.
And I'll tell you that for me, the best thing that's ever happened to me in my professional career was having the ability to actually go down in the ocean, go down in deep water, because you see things that you've read the literature, and in the past all I had ever seen were samples that had been dredged up, and when you see them it's like, oh my gosh, that's what it really looks like. And you get a whole different perspective. And one of the reasons that we invited Bill to be part of our team was to get a feel for what I and my colleagues who had the opportunity to go down in the sea, is there something that's giving us kind of an edge over the early career scientists and the students, so that we know what to anticipate. We know what to say, just go back that way because we've been there. Conversely, these young scientists have grown up doing kind of robotics, and so what can we learn from them as well? And that's really been something that I've been very interested in, having Bill analyze and being present for yeah. But yes, I think there's still a need to go down.
And I would think from all that we know, we're not going to be going to Mars for the science. We're going to go because we want to be there. We want to explore.
Because it's exciting.
We want to walk. You saw those pictures.
It's just exciting.
It's a very inviting place.
Okay.
On that note, thank you.
Thank you. Thanks very much.